Today we're exploring a fascinating, sometimes hilarious, and occasionally frustrating chapter in the development of autonomous vehicles, Waymo's AI taxis. Waymo, Google's self-driving car spin-off, has been at the forefront of deploying fully autonomous vehicles for commercial use. These cars promise a future where transportation is safer, more efficient, and available to everyone, all without a human driver behind the wheel. However, real-world deployment has proven that autonomous driving is not without its comedic and sometimes perplexing moments. In this video, we'll break down recent incidents that highlight both the potential and the pitfalls of AI-driven mobility. From robbers inadvertently turning themselves in to vehicles getting stuck in endless loops, these stories provide valuable lessons for AI, law enforcement, regulators, and everyday passengers. By examining these incidents in depth, we can better understand the capabilities and limitations of Waymo's AI, the software and hardware challenges, the regulatory implications, and the broader trajectory of autonomous transportation. Let's dive into the real-world stories that are shaping the future of self-driving cars. Let's begin with one of the most ironic and attention-grabbing incidents involving Waymo's autonomous taxis. The case of a robber in Los Angeles who attempted to use a self-driving car as his getaway vehicle. At first glance, this might seem like a plot from a comedy or a Hollywood movie, but it is a real-world event that highlights the unexpected interactions between autonomous technology and human behavior. The robber's plan was straightforward, at least in his own mind. After committing a store robbery, he presumably thought that a driverless taxi would provide the perfect escape. Without a human behind the wheel, he could avoid law enforcement and perhaps exploit the novelty of AI technology to evade capture. From the perspective of someone unfamiliar with how Waymo's vehicles operate, this plan might have seemed clever. Autonomous cars follow programmed rules, after all, so he may have assumed they wouldn't interact with external factors like police lights or sirens. However, Waymo's AI is designed with safety and situational awareness at the forefront. The vehicle's sensors constantly monitor the environment, including traffic signals, pedestrians, other vehicles, and critically, emergency services. In this case, as the robber attempted to flee, the car detected flashing police lights and heard the sirens. The AI recognized the presence of law enforcement and executed pre-programmed protocols for such scenarios. It brought the vehicle to a stop in a safe location and engaged its communication system to alert authorities if necessary. This resulted in an outcome that was not only unexpected for the robber, but also highly effective from a law enforcement standpoint. The suspect was effectively delivered directly to the police without any human intervention. From a technological perspective, this demonstrates the sophistication of Waymo's object detection, environmental mapping, and real-time decision-making capabilities. The vehicle was able to integrate multiple sensory inputs, interpret the situation accurately, and take autonomous action to ensure compliance with the law. It's also important to understand the broader implications. This incident shows that autonomous vehicles are not simply passive tools. They can act in ways that influence human behavior and legal outcomes. In a sense, the AI became an active participant in enforcing the law, a role traditionally reserved for human drivers and law enforcement officers. This raises important questions. Should autonomous vehicles be allowed to intervene in criminal activity? What are the legal liabilities if the AI's decision-making leads to unexpected consequences? Who is responsible, the manufacturer, the software developer, or the vehicle owner? These questions are actively being debated as regulators, lawmakers, and technology companies grapple with the rapid deployment of AI-driven transportation. From a narrative standpoint, the story is both humorous and instructive. There's a certain irony in a criminal attempting to use cutting-edge technology to evade justice, only to be foiled by that very technology. But beyond the humor, The incident serves as a real-world case study in AI ethics, design robustness, and the unforeseen interactions between humans and autonomous systems. Technically, the success of the AI in this scenario is built on multiple layers of innovation. Waymo's vehicles combine LiDAR, radar, and high-resolution cameras to perceive their surroundings in real time. These sensors feed into sophisticated algorithms that allow the car to detect objects, predict their behavior, and plan safe trajectories. The AI also maintains a detailed internal map of the environment and can cross-reference dynamic events like emergency vehicle movements against expected traffic patterns. In this case, the car's rapid recognition of police activity and its decision to stop demonstrate the maturity and reliability of these integrated systems. Now, let's step back and look at the broader evolution of self-driving services, which provides context for incidents like the robber's ride. Autonomous vehicles have come a long way over the past decade. Early systems were limited to advanced driver assistance features, lane keeping, adaptive cruise control, but fully autonomous taxis were still experimental. Waymo, alongside Tesla, Cruise, and others, has pioneered true robo-taxi services, gradually rolling out cars capable of navigating complex urban environments without a human driver. These services rely on a combination of LiDAR, radar, cameras, and sophisticated AI to perceive the environment, make split-second decisions, and plan safe routes. The evolution has been iterative. Software improvements, real-world testing, and thousands of miles of supervised driving gradually built confidence. Waymo's fleet, for example, communicates not just with passengers, but with external systems, like traffic signals and law enforcement, creating a connected ecosystem of autonomous mobility. This evolution explains why these vehicles can both prevent crimes, like delivering the robber to police, and occasionally create hiccups, like looping endlessly or taking illegal turns. Each incident feeds back into the AI, refining decision-making algorithms and safety protocols. Overall, the progression from semi-autonomous features to full robotaxi deployment is a testament to the growing sophistication of AI in transportation. It highlights both the incredible potential and the real-world challenges that still need careful management as these services scale. In this slide, we look at Waymo's support system and how it responds to real-world issues. Take the example of Mike Jones in Los Angeles, whose Waymo ride got stuck in a looping circle of death while trying to reach the airport. Frustrated and feeling unwell, he contacted Waymo support. Waymo's response team quickly intervened, remotely diagnosing the software glitch that caused the endless loop and implementing an update to resolve it. The company also refunded the passenger, demonstrating accountability and customer care. This incident highlights the growing role of human oversight in autonomous vehicle operations. Even as self-driving technology advances, remote monitoring and support remain critical to maintaining safety, reliability, and public trust. Each intervention provides valuable data that feeds back into software improvements, helping Waymo refine route planning, error detection, and emergency protocols. In essence, Waymo's support framework turns real-world mishaps into learning opportunities, accelerating the evolution of autonomous ride services and ensuring that both safety and customer satisfaction continue to improve. When we examine autonomous taxis such as Waymo, we encounter a fascinating duality. These vehicles are simultaneously impressive feats of artificial intelligence and autonomous control, yet also prone to errors and unpredictability that remind us how early we are in this technological revolution. On the positive side, incidents such as the Los Angeles robber illustrate the unique advantages these vehicles provide. The robber attempted to flee the scene of a crime by entering a Waymo self-driving taxi, likely assuming that the car would function like a conventional vehicle, merely transporting him wherever he wished without oversight. Instead, The vehicle's AI detected the flashing lights and sirens of nearby police, and using its real-time environment recognition capabilities, reacted by stopping safely and alerting authorities. This incident serves as a real-world example of how autonomous vehicles can act as intelligent agents in society, not just as transportation tools. They can integrate data from cameras, LiDAR sensors, radar, and onboard GPS mapping to make dynamic decisions in complex environments, such as recognizing emergency vehicles or detecting unusual driving behavior. The implications of such capabilities are profound. Autonomous taxis are not merely replacing the human driver, they are acting as autonomous decision-making entities. In the robber case, the AI essentially made a judgment call that balanced safety, legal compliance, and public responsibility. The car prioritized public safety over the desires of the passenger, demonstrating a level of ethical and procedural reasoning embedded in its programming. For law enforcement, this opens new possibilities. Self-driving fleets could function as supplemental public safety agents, providing real-time reporting, automated compliance, and even deterrence of criminal activity in urban areas. It also reflects the potential for AI to contribute positively to society beyond convenience and mobility by supporting law enforcement, improving response times, and reducing the risk to human drivers. However, as we delve deeper into the real-world performance of autonomous taxis, we see the other side of the coin, unpredictability and occasional failures that highlight the current limitations of AI. Take the case of the Circle of Death ride, where a passenger in Los Angeles experienced a vehicle endlessly circling while attempting to reach the airport. For the passenger, this was not just an inconvenience, it was a stressful and disorienting experience, leading to feelings of frustration and even physical discomfort. While the software glitch was ultimately corrected through intervention by Waymo support, the incident underscores that autonomous systems are not yet perfect. Even with advanced sensor arrays, real-time mapping, and predictive navigation algorithms, self-driving cars can misinterpret routing instructions, encounter edge case scenarios, or experience software errors that human drivers would immediately correct instinctively. Similarly, the incident in San Bruno, where a Waymo vehicle attempted to avoid a DUI checkpoint, illustrates a unique regulatory and legal challenge. The AI lacked the human context to understand the legal implications of its actions. While humans would know that evading a checkpoint is illegal and could result in serious consequences, the AI simply followed its programmed instructions to optimize routing and efficiency. The absence of a human driver creates a regulatory gray area. Who is accountable when an autonomous vehicle violates the law? Authorities have begun considering legislative changes that would allow companies like Waymo to be fined or held responsible for such incidents, but the question of liability remains complex. This duality, vehicles acting intelligently, yet sometimes misunderstanding legal or social norms, represents one of the central challenges of integrating autonomous taxis into public infrastructure. From a technological perspective, these incidents highlight both the promise and the limitations of AI decision-making. On the one hand, Waymo's ability to respond to police lights or detect unusual activity demonstrates an advanced level of environmental awareness and autonomous reasoning. On the other hand, when the AI misinterprets a situation, such as the endless looping ride, it reveals that machine learning models are still heavily dependent on the quality of training data, edge case coverage, and continuous updates. In real-world applications, AI systems must contend with countless unpredictable variables, pedestrian behavior, construction zones, erratic human drivers, temporary road closures, and even weather-related challenges such as rain, snow, or fog. Each variable represents a potential failure point, which engineers must anticipate, simulate, and address through continuous software refinement. Another important aspect of this duality is the user experience. While autonomous taxis offer convenience, accessibility, and potential safety benefits, users remain highly sensitive to perceived reliability. In the examples we discussed, passengers who experience glitches, even minor ones, may lose confidence in the system. Trust is critical for the adoption of self-driving services, yet trust is fragile when AI systems occasionally behave unpredictably. Waymo and other autonomous vehicle providers must therefore invest not only in technological advancement, but also in user communication, real-time support, and contingency protocols. This includes mechanisms such as human support agents who can remotely intervene, customer service guarantees like ride refunds, and ongoing software updates to prevent recurrence of similar incidents. The circle of death scenario, while humorous in hindsight, represents an important lesson in how perception shapes public acceptance of AI technologies. Furthermore, these incidents provide a rich source of learning and continuous improvement for autonomous vehicle development. Each anomaly is carefully logged, analyzed, and fed back into the AI's training pipeline. For example, a vehicle that misinterprets a traffic scenario contributes to a better understanding of rare edge cases, allowing developers to refine algorithms to handle similar situations in the future. Over time, this iterative process improves safety, predictability, and user satisfaction. In a sense, the real-world errors are as valuable as the successes because they illuminate the gaps between simulation and reality, highlighting where human intuition and AI reasoning diverge. In conclusion, the dual nature of autonomous taxis is both their greatest promise and their most significant challenge. On one side, they can act as intelligent, law-abiding agents capable of enhancing public safety, efficiency, and accessibility. They represent a fundamental shift in how transportation systems operate, with the potential to reduce accidents, improve traffic flow, and democratize access to mobility. On the other side, they remain fallible, susceptible to software glitches, edge case failures, and regulatory ambiguity. The tension between technological capability and real-world unpredictability defines the current landscape of autonomous vehicles. For users, policymakers, and industry stakeholders, this duality underscores the importance of measured adoption. Autonomous taxis should be integrated with clear safety standards, robust oversight, and continuous feedback loops. At the same time, society must recognize the potential of these systems to transform mobility, safety, and urban planning. By embracing the dual nature of AI-driven vehicles, acknowledging both their strengths and limitations, we can guide their development responsibly, ensuring that these technologies deliver maximum benefit while minimizing unintended consequences. Ultimately, the story of autonomous taxis like Waymo is a story of learning, adaptation, and gradual perfection. Each ride, each error, and each success contributes to a broader understanding of how AI interacts with the real world. The dual nature of these systems is not a flaw. It is a feature of an evolving technology that must navigate the unpredictable complexity of human environments. Understanding this duality is key for anyone interested in the future of mobility, AI adoption, and urban innovation. As we examine the ongoing evolution of autonomous vehicles like Waymo, it becomes clear that real-world incidents, both minor glitches and serious operational challenges, play a critical role in advancing the technology. Unlike traditional software, which often functions in controlled digital environments, self-driving cars operate in highly unpredictable real-world conditions. Every ride is essentially a live experiment, and each incident provides invaluable data for improving the AI systems that drive these vehicles. Let's start by revisiting some of the examples we've discussed earlier. The Los Angeles robbers scenario demonstrated how Waymo's AI can positively influence public safety, stopping the vehicle and alerting authorities. Meanwhile, the Circle of Death ride and the San Bruno DUI checkpoint scenario highlighted how the system can misinterpret routing instructions or fail to account for legal and regulatory context. These incidents, though seemingly isolated, are far more than anomalies. They are opportunities for refinement. In essence, every misstep by an autonomous vehicle is a case study that informs engineers about edge case behavior, environmental variables, and human interaction patterns. From a technical standpoint, incidents feed into a structured learning pipeline. Waymo and similar companies employ continuous feedback loops, where every real-world anomaly is logged, analyzed, and fed back into the training datasets for machine learning models. For example, the circle of death ride would prompt engineers to examine why the AI repeatedly misread the routing instructions or failed to detect the intended destination. Was it a mapping issue, a sensor misreading, or a flaw in the decision-making algorithm? By dissecting the incident down to its technical components, engineers can update the AI's predictive models, adjust routing logic, and improve decision-making under similar circumstances in the future. This process exemplifies what AI researchers call reinforcement learning from real-world feedback. Moreover, incidents help developers understand the interaction between AI and human behavior. Passengers can act unpredictably. They might cancel a ride mid-trip, input ambiguous destinations, or attempt to override vehicle instructions. Similarly, other road users, like cyclists, pedestrians, and human drivers, behave in ways that are difficult to fully simulate in virtual environments. Each incident provides a live laboratory to capture the nuances of these interactions, enabling the AI to better predict and respond to human behavior. Over time, this iterative learning reduces errors, improves passenger experience, and builds trust in autonomous systems. Incidents also serve as testing grounds for regulatory and operational policies. The San Bruno DUI checkpoint example illustrates a scenario where current traffic laws did not account for autonomous vehicles. While no human driver was present to issue a ticket, the situation sparked discussions with lawmakers and regulators about how companies can be held accountable, how fines or penalties might be applied, and what safety measures need to be mandated. In this sense, real-world incidents push both technology and policy forward in tandem, shaping the ecosystem in which autonomous taxis operate. They reveal gaps not only in AI performance but also in legal frameworks, insurance requirements, and public safety protocols. Another important dimension is user feedback. Passengers who experience glitches, delays, or unexpected behavior provide subjective insights that pure telemetry data cannot capture. Complaints about discomfort, confusion, or perceived risk offer engineers valuable information about usability, human-machine interaction, and the emotional impact of autonomous vehicles. For instance, the circle of death ride might have been technically safe, but the passenger's frustration indicates that the system must also consider psychological comfort and perceived control. By integrating this feedback, companies can refine user interfaces, improve ride notifications, and develop better real-time communication systems between the vehicle and passengers. Financially, learning from incidents is also crucial. Each real-world failure that is corrected and documented reduces the likelihood of catastrophic accidents that could lead to lawsuits, insurance claims, or reputational damage. In the highly scrutinized autonomous vehicle market, public trust is tightly linked to financial sustainability. Companies that effectively turn incidents into learning opportunities not only improve safety, but also protect their market valuation and investor confidence. In other words, continuous improvement through incidents is as much an economic strategy as it is a technological one. The scale of data involved in this process is staggering. Waymo's fleet collects millions of miles of driving data every year. Every braking event, sensor reading, routing decision, and anomaly becomes a piece of the puzzle that helps the AI learn faster than any human driver could. When aggregated across a fleet, these incidents create a comprehensive knowledge base that accelerates the development of robust, adaptable, and highly reliable autonomous systems. This is a key advantage of autonomous fleets. The more they operate, the smarter and safer they become, turning incidents into engines of progress. We also need to consider the ethical implications. The fact that AI learns from incidents raises questions about transparency, accountability, and bias. Engineers must ensure that the AI's learning process does not inadvertently encode unsafe behaviors or discriminatory decision patterns. By systematically analyzing incidents, companies can validate the fairness, safety, and ethical compliance of their algorithms. For example, if a pattern emerges where certain pedestrian demographics are more likely to be misclassified by sensors, engineers can adjust models to correct this bias, ensuring equitable safety outcomes. Finally, the concept of improvement through incidents extends beyond individual vehicles to the broader transportation ecosystem. Each glitch or anomaly informs city planners, regulators, insurance companies, and emergency responders about how autonomous vehicles behave in complex environments. This collective learning contributes to smarter urban planning, safer infrastructure design, and more effective traffic management policies. In other words, incidents with one autonomous taxi fleet can generate knowledge that benefits the entire mobility industry, creating a positive feedback loop for innovation and public safety. In conclusion, the duality of autonomous taxis, being both highly capable and occasionally fallible, becomes a powerful engine for improvement. Real-world incidents, far from being purely negative, serve as the primary mechanism through which AI systems evolve. They inform technical refinements, regulatory adaptation, user experience enhancements, ethical safeguards, and industry-wide best practices. Companies like Waymo demonstrate that learning from these events is not just reactive, it is a deliberate and structured approach to accelerating progress. As autonomous taxis continue to operate and accumulate miles, the lessons derived from incidents will steadily reduce errors, improve trust, and enable AI systems to operate with unprecedented reliability. This iterative, data-driven improvement process is central to realizing the promise of autonomous mobility, where vehicles are not only self-driving, but also continually learning and evolving in response to the challenges of the real world. By embracing incidents as a learning tool, the autonomous vehicle industry positions itself for long-term safety, innovation, and societal benefit.